Greetings everybody, and welcome back to some more complex analysis. I'm done with exams, so now I have plenty of time hopefully to record videos for you guys. What are we doing today? We're taking a look at this integral from minus infinity to infinity of log of x squared plus 1 over x squared. So it doesn't look particularly nice because of that logarithm, but it turns out this is a pretty cool integral to evaluate, and we'll see how that works later. So first of all, how do we usually get started with these? Well, we like to define some kinds of complex function to integrate. So why not just define our function f of z to be not just the integrand, but we're going to replace all the x's with z's. So first of all, we're going to let f of z here be a new complex function and be equal to, we just have the logarithm of z squared plus 1 over z squared. That's our complex function. Now, before we go any further with this, I do want to massage this expression somewhat, rewrite it in terms of a slightly nicer form that will be useful later. First of all, notice we have z squared plus 1. And, well, z squared plus 1, if you've done a bit of complex numbers before, you may notice you can factorize this into z plus I and z minus I. So that's exactly what we're going to do here. We will notice that this is exactly equal to, and we have the logarithm of, well, big bracket, and then we're going to have z plus I, and then we have a z minus I like so. And then on the denominator, this is still going to be divided through by z squared. And now what we can do is use logarithm properties to split the products inside there into the sum of logarithms. So if you do that, what are we going to get? Well, we're going to get precisely the logarithm of, that's going to be z plus I, and then we have plus the logarithm of z and then minus I, and all of this is still divided through by z squared. Okay, now we have logarithms of complex things in there, so we want to use the definition of the complex log. We're going to write it in terms of the real imaginary parts, because that's how we're going to produce the argument function, which will be very important later. So how do we rewrite log of complex numbers? Let's put it up over here maybe. So just the side notes here, if we have the logarithm of a complex number, let's say z, then we can rewrite this as the logarithm of the magnitude of z, or the absolute value of z, or the modulus of z whatsoever, and then you have plus I times the argument of z. So log of z is actually multi-valued, and what we're going to do is we're just going to choose some kind of branch of log. It could be the principal branch, that's what we usually use. However, we can choose any branch really, and we make that choice via this argument. So you can define your arguments to be, for example, from 0 to 2 pi or minus pi to pi, but as long as you're consistent, it really doesn't quite matter. So we're going to apply that down over here with the two logarithms. What we're going to have is, let's bring up this blackboard, we're going to have the logarithm of absolute value, or modulus. I should probably say modulus. I think that's the correct terminology when you work with complex numbers. We have z and then plus I, and then we have, well, I'm going to do this guy next, so that's going to be plus the logarithm of absolute value modulus of z minus I, and then we have plus the argument. I need to rub out that z squared there, I put that a little bit too low. And then we have plus I times the argument. So we have a plus I times the argument of this first guy, so that's going to be argument of z plus I, and then we have plus I times the argument of the second guy, which is a z minus I, like so. And all this is still over z squared. I guess I'll just put brackets over here and then divide by z squared, just so I don't have to draw a big denominator or fraction line, whatever that's called. And what can we do from here? Notice with these two logarithms, we can kind of combine them once again if we really wanted to. So this is going to be equal to logarithm. And if you combine these modulus together, well, you're just going to get a z squared plus 1 once again inside of modulus. So this is modulus of z squared plus 1. And then we have plus I. And we can factor out I, and we can put the arguments inside. So this is going to give the arguments of z plus I. And then we have plus the arguments of z minus I. And you can't really simplify the sum of the arguments any more than this. And all of this is finally all divided through by z squared. So this is how we can rewrite our complex function f of z. Now the next thing we do need to do is make a pick of which arguments we need to use, because we have two logs We have two args, we have to pick the branches for each log. Now before we do that though, we need to take a look at what we're integrating because we want to choose rather, branches or branch cuts that are useful for our contour integration. So let's put the picture up over here somewhere. So let's say this is the complex plane. What are we integrating exactly? Well, we want to integrate from minus infinity to infinity. So let's start at some big radius negative r here, and then we're going to go all the way up to r. Hopefully make this symmetrical enough. So we want to integrate along this path here, and we're going to call that path, I really don't know, let's just call it omega. Why not? Okay. Now, you'll notice one thing, we have these arguments, and these aren't exactly centered at 0, they're actually centered at, well, the first one, this is centered at minus I, and the second one that's centered at I. So in fact, we're going to pick up two branch points at plus or minus I, and I'll put that in blue here. I found some colored chalk in this tutorial room or lecture room, so we can use color on the blackboard now. We don't have poles today, usually I'll do those in red, but we have branch points and branch cuts, which I'll do in blue. So these two guys, this is I over here, and this guy down here, this is negative I, okay? So we want to integrate along this path. So what exactly, or how exactly should we choose our branch cuts exactly? They're going to be originating from plus and minus I, and we can choose any direction we want for the branch cuts. Probably the most useful one is if we orient, let's say, the top one upwards like so. So this is our branch cut, and then we have another branch cut that goes down over here. Now, it really doesn't quite matter how you orient it. You could really orient it like on a 45-degree angle like that if you really wanted to. This one, you could orient it that way because it doesn't really interfere with this path from minus r to r. But yeah, we're just going to choose this setup over here. We don't want the branch cuts to be going through this line from minus r to r because we don't want to have multiple values and a discontinuous jump on our contour integration path. So what we're going to do, we want to turn this into a contour. We have a straight line here, so how exactly do we usually complete the contour? Well, we're just going to use a semicircle, but then we run into a bit of a problem because, well, we don't want to pass through this branch cut. That's no good over there. So what we're going to do, we're going to attempt to make a little semicircle out of this, like we usually would when we integrate from minus r to r, but we're not going to go all the way into that branch cut, except we're going to stop a little bit of a distance before that, maybe some epsilon distance, and then we're going to go down here. So we're going to go down like so, and then we're going to encircle this branch cut, or this branch point rather, and let's put the minus sign somewhere else later. We're going to encircle this guy, make a little loop around it like so, and then we're going to come back up over here, and then this, we're going to complete the contour like so. So it's a nice little keyhole contour inside of a semicircular contour. Don't think I've done any of these, at least not that I know of. So how exactly is this going to work? We're going to go this way, we're going to go up along this path, down along here, around this little circle, we're going to go back up again, and then down to finish off the contour. Okay, so let's call this contour here, let's just call it C. We're going to call this path here gamma. And I need to put that I back up over here, so let's just put it, yeah, let's just put it here, that's our I, and then let's call the path going inwards over here, let's call that the psi 2, and this guy is at psi 1, and then we have gamma 2, and then gamma 1 like so. All right, so this is our setup here, so we know exactly what we want or how we want to choose our branch cuts. So what exactly are they going to be? So let's put the branch cuts over here. We want arg of z, let's do the z minus I one first. Arg of z minus I, and that's going to be on the interval. Well, we want to start, let's say pi over 2 here. We're going to start on the left-hand side of this. We're going to start at pi over 2, and then we're going to go all the way around to the, if you add 2 pi, that's going to be, well, 5 pi over 2. So that's the first guy, and then how about the second guy here? We want the argument of z plus I, that's going to lie on what interval? Well, that's down over here. We want to swing from, let's go from minus pi over 2 all the way to 3 pi over 2. I think that should work out quite well. So we have 3 pi over 2 here. And yeah, maybe I think I said this before, it doesn't really matter how you pick the branch cuts over here or the arguments, as long as you're consistent throughout your solution, then everything should work out perfectly. So really, I could have picked, let's say, I don't know, 5 pi over 2 to, what's that going to be, 9 pi over 2 or something, and that's going to work out the exact same way. Okay, so we have a bunch of integrals. We know what our contour should look like. Let's go ahead and start integrating things, and I don't need this blue chalk anymore. So first of all, inside the contour C, everything's nice and analytic and holomorphic. So the contour integral is just going to evaluate to 0. So let's put all that on this side. So first of all, we know that 0 is equal to the contour integral over C of our function f of z dz. Okay, now we know that we can decompose our contour C into multiple parts. In particular, we have the path running from minus r to r, which we called omega, but yeah, I'm just going to write integral from minus r to r. And then what else do we have? We have the path along gamma 1 and gamma 2. So we have plus, integral over gamma 1. I guess we'll just do psi 1 and psi 2 first. Psi 1 and then psi 2. And then we have plus the integral over gamma 1. And then plus the integral over gamma 2. And then we have plus the integral over little gamma, which is that little circle in the middle there. So those are all our integrals we're going to be evaluating. And yeah, we might as well start doing them one by one. And let's call this integral at the very start I as well, because, first of all, the integral from minus r to r, if you take the limit on this guy, you're just going to reproduce I. It's pretty easy to see that. And so I guess what we'll do, we have 0, so in the limit as r approaches infinity. And I guess if we call some of these parameters epsilon, which control the size of these little paths, I guess we'll take epsilon to 0 as well. So in the limit, we're going to have colons. So what happens if we take the limit? We're going to have 0 being equal to this first integral that's going to evaluate to I. Okay, and we just then evaluate all the other ones as well. We'll do that on the next blackboard. So which integral should we do first? Where's the blackboard? There it is. So let's do the integral over little gamma first. Let's get that out of the way. That one's going to vanish because we're integrating around a little branch point there. And if you integrate around a branch point, you're just going to get 0. So nothing really interesting happens there. So first of all, let's do that. Integral over little gamma. Well, how exactly is that going to work? We might as well put all our parameterizations on this blackboard as well. So first of all, how do we parameterize little gamma? Well, little gamma, we'll notice that all the z's on there, well, that's just a little circle around the pointer I, so we can write that as z being equal to I, and then we just add a little circle of size epsilon, let's say, so epsilon e to the I theta. So therefore we have, first of all, where does theta start and end? Well, it starts at, and that's going to be pi on 2 in the limit, and then we're going to go all the way to 5 pi on 2. So theta on the interval pi on 2, and we're going to go to 5 pi on 2. And we also have that dz. What exactly is that? That's going to be, well, if you differentiate this guy, that's I epsilon e to the I theta. That's just a bit of a chain rule. So yeah, I epsilon e to the I theta, and then we have a d theta to finish off. That's our gamma parameterization. So let's plug that into our integral here. So integral over gamma, what exactly is that going to be? Well, we're going to have the integral, we said, from pi on 2 all the way up to 5 pi on 2. Okay, and we put in our function, so that's going to be a logarithm. We have, well, what do we usually have? We have z squared plus 1. But instead of z, we're going to have the epsilon e to the I theta. So z is that guy. So we have I plus epsilon e to the I theta. This is squared, so this was our z here, and then we have plus 1. And all of this, that's divided through by, let's say, z squared. So z squared, that's going to be the I plus epsilon e to the I theta. And this is squared here. And then dz, that's I epsilon e to the I theta. And then we have a d theta. So how on earth do we simplify this here? Well, first of all, we have epsilon e to the I theta in the limit as epsilon goes to 0. This guy's just going to vanish off, so that's 0. And then we're left with I epsilon times some stuff with this logarithm. let's see what we can do with that in particular. Well, first of all, it's probably better to write this logarithm in terms of the sum of the two logarithms like we had on this line here, because then we can avoid that square there, which is a little bit nasty. So let's go ahead and do that. So we just have the integral. I won't bother writing the bounds, they're not too important. We're going to have, logarithm of, it was originally this guy minus I, and then this guy plus I. So logarithm of this guy, so I plus epsilon e to the I theta, we have plus I, and then I think we have, that's going to be plus the logarithm of the same guy again, so I plus epsilon e to the I theta, but then we have a negative I over here. And all of this, that's going to be divided through by, well, if you just start taking limits bit by bit over here, and we have, well, that's just going to be -1 on the denominator, because that's I squared pretty much. And then we have, well, I over here, epsilon e to the I theta, and then we have a d theta. Let's bring this I and this -1 out to the front because they're not being super useful. So we have a negative I over here, I guess, in the limit. So we don't really need this denominator. So next up, what can we do? Well, this I and this I will cancel, and we're going to be left with log of epsilon and then plus I times theta. You can just use your log properties there. So this is going to give us the integral. We have the logarithm of what we have. We have 2I, and then we have plus epsilon e to the I theta, and then we have, that's going to be plus. We have the logarithm of epsilon, and then we have plus I times theta because log and the e cancel. And yet, in fact, you can do that because of this logarithm. This was the logarithm centered around this point over here, this I. And the argument we chose for that was from pi on 2 to 5 pi over 2, right over here. And that turned out to be exactly the bounds of our integrals. So theta can only go from pi on 2 to 5 pi on 2, so we're fine just to cancel log and e there. In general, you can't do that. You have to be a bit more careful. So that's what we have, and then we have the epsilon e to the I theta. That's multiplied into everything here. So this is all multiplied by epsilon e to the I theta d theta. And now this factor of epsilon is actually really quite nice because it's in particular going to kill off this guy. It's going to kill off, well, in the limits as epsilon approaches 0 here, that's going to vanish. Log of 2i, that's some complex number. So this is going to go to 0 as well because of this epsilon. And the only thing we need to worry about is what on earth happens to log epsilon times epsilon. Because as epsilon goes to 0, this is infinity, or negative infinity. As epsilon goes to 0, this is 0. So we do have to be a bit careful with this. Luckily, L'Hopital has us sorted. So if you take a look at the limit as epsilon approaches 0 of log of epsilon, and now instead of multiplying by epsilon, I'm going to divide by 1 over epsilon, just so we have it in infinity over infinity, and using L'Hopital's rule over here, if you differentiate the top, that's going to become, let's see, that's going to become 1 over epsilon. Differentiating the denominator, that's negative 1 over epsilon squared. So this is the limit as epsilon approaches 0 of negative epsilon, but that is going to be equal to 0 in the end. So assuming you can bring the limits inside of the integral, you should be able to do this in this case. You can, if you really wanted to, you can find some bounds for that function. So you can use dominated convergence theorem whatsoever, and you can bring the limits in, take the limits on the inside of the integral, and log epsilon times epsilon in the limit as we approach 0. In the limit as epsilon approaches 0, well, everything's just basically going to go to 0, which is what we're expecting because integrals around branch points go to 0 as you make that circle really, really, really small. Okay, so what should we do next? Let's take a look at the integral over psi 1 and psi 2. These two integrals are going to be pretty interesting, I tell you. Some things are going to cancel out really nicely. So you'll see how that works very shortly. So let's do the integral over psi 1 and psi 2, and we're going to in fact do these two together because it just works out nicely that way. So we have the integral over psi 1, and then we have, how should I do this? And then plus the integral over psi 2. So let's see what this gives us here. Well, this is just going to give us the integral over psi 1 first of all of f of z. Now, in particular, with the integral over psi 1 and psi 2, we're going to be approaching this branch cut up over here, which means we have to be very careful as to what the arguments of our logarithms approach, because, yeah, the value of the integral is highly dependent as to which way you approach it. So in particular, these two parts aren't going to cancel out. And to do that, we're actually going to use this form of the function f of z, which we derived at the start of the video. So let's see what this gives us if we plug this in to our integral. So first of all, we have the integral over psi 1 of the logarithm of z squared and then plus 1, and then we have plus I times the argument of z plus I. Now, this is where we have to be careful. What exactly is the arg of z plus I approaching as we approach from the left-hand side? This is the most annoying. Blackboard over doesn't want to stay still. There it goes. If I put it down there, it stays still. So arg of z, what was the first one? Z plus I, right? Arg of z plus I, that's centered around here. As we approach the left-hand side of this branch cut, what is arg of z plus I approaching? Well, it's defined from minus pi on 2 to 3 pi on 2. So hopefully you can convince yourself, well, this is minus pi on 2, and we're approaching somewhere up here, so that has to be pi on 2. It doesn't matter which way you approach, it's going to be pi on 2. So this guy over here, that's going to be pi on 2 to begin with. So that's the arg of z plus I. Now how about the arg of z minus I? Well, z minus I, that's centered around here. What's the argument approaching as we come from the left-hand side? Well, how is this guy defined? Well, that's going to be pi on 2 to 5 pi on 2. So as we approach from the left-hand side, we're decreasing our arguments. So we're actually going to approach this pi on 2 down here. So we have a plus and pi on 2, which is quite nice. So plus pi on 2. Okay. Now we also have the integral over psi 2 we need to take care of, and this third blackboard just does not like staying still for some reason. So all of this is still divided through by z squared. Z squared is nice and continuous. It's going to approach the same thing no matter which way we approach things. So we have a dz here, and then let's do the integral over psi 2. Let's do it down here. Why not? So we have the integral over psi 2. Now on psi 2, we're approaching from the right-hand side. So this is going to give us the logarithm of z squared, and then plus 1 once again. And then we're going to have plus I times, what was the first thing? We have plus I times the argument of z plus I. So once again, it doesn't matter if we approach from the left-hand or right-hand side down here. From this guy's perspective, we still approach pi on 2. So that's going to be pi on 2 right over here, I guess. So that's pi on 2. And then we have plus the argument of z minus I. Now from this guy's perspective here, that's going to be dependent on which way we approach things. So as we approach from the right-hand side, that's increasing our arguments. So in fact, we're going to approach 5 pi on 2 here. So we have a 5 pi on 2 right over here. Okay, and this is all, once again, still divided through by z squared, and then we have a dz. Okay, that's quite nice. Now, we need to observe one thing. Absolute value, or modulus of z squared plus 1, that's continuous everywhere. And if you take the logarithm of z squared plus 1, well, you're just taking the logarithm of a real number. So in fact, this guy is continuous everywhere. So the logarithms of these absolute values over here, they approach the same value no matter which way you approach the branch cut type over there, which is really quite nice. So the only thing that changed here were pretty much this pi on 2 and this 5 pi on 2. So if we take the limits as psi 1 and psi 2 approach each other on that branch cut, then notice one thing, psi 1 and psi 2, they're just going to be integrals that go along the same path pretty much, but they just go in the opposite directions. So in particular, in the limits, what we can do is instead of writing psi 2 here, we can just say, well, this is really the same thing as psi 1 in the limits in terms of the path we're integrating along. But because this is oriented in the other direction, we just need to put an extra negative up over here. And this is really quite nice here because we have an integral minus an integral. These are the same path we're integrating along, so we can combine these integrands together. And in particular, what happens is these logarithms, those are going to cancel because it's the same thing. So log and log these will cancel. And we have pi and 2, these will cancel because, again, we're subtracting. So bang, bang, these cancel. And then what survives out of all this cancellation? The pi on 2 and the 5 pi on 2, because we approach different numbers here, depending on which side of the branch cuts we're on. So overall, this is equal to, we have integral over psi 1. We're going to have I out the front. We can factor the I out of both the integrals, so let's put it over here. We have pi on 2, and then we're going to subtract off 5 pi on 2. What is pi on 2 minus 5 pi on 2? That's 2 pi, I believe. So we have negative 2 pi I out the front. We can factor out the constants. And then we have the integral over psi 1 of, well, we're just going to be left with, well, 1 over z squared. So 1 over z squared goes in here, and then we have a dz, like so. All right, so this was a pretty cool thing that happens here. I always love it when the logs cancel. In fact, your logs are always going to cancel when you approach on different sides of the branch cut in two different orientations. Well, again, it's highly dependent on what function you use, but if you just use log or log squared or something, then the main parts will always cancel out. Okay, so the only thing that's left for us to do is to evaluate that integral there, which really isn't too bad to do. Psi 1, that is a path going upwards in the complex plane, so we can parameterize that quite easily. Let's do it over here. So psi 1, how do we parameterize this? Well, we notice that z, that is equal to I times t, where t, that's going to go from 1 up to infinity, pretty much. So t on the interval, we have 1 to infinity, and then our dz, that is going to be equal to dt, pretty much, or actually I times dt. Okay, so if we plug all of this stuff in, what are we going to make of this integral here? Well, this is going to become the integral, or negative 2 pi I. We're going to have the integral, that's going to go from 1 up to infinity, and we have 1 over z squared, but what is z? That's this I times t, so we have I times t, and this guy is squared here, and dz, that's going to become I times dt. Okay, and this integral, this is going to converge nicely here, integral from 1 to infinity of something over t squared, so this is going to be negative 2 pi I. We have, first of all, I squared, that's negative, so that's going to cancel with this negative here, so let's get rid of that guy. We have the integral from 1 to infinity, 1 over t squared, okay, and then we have I, but I can jump out to the front, so times I over here, and we have a dt, like so. Okay, let's evaluate this integral, nice, real, and easy integral. So I times I, first of all, that's a negative, so we have minus 2 pi. Not 2 pi I, just a 2 pi, so negative 2 pi. And then we have the integral from 1 to infinity of 1 over t squared, but what's the antiderivative? It's negative 1 over t, and we go from 0, well not 0, we go from 1 to infinity. If you plug infinity into here, you're going to get 0. If you plug 1 in, you're going to get a negative 1, but because that's the second part of the fundamental theorem of calculus, we also pick up an extra negative. So overall, this guy in here, that's just going to evaluate to exactly 1, leaving us with a nice answer of negative 2 pi, which is pretty cool. Okay, so what we've just done, we've just evaluated these two integrals. Psi 1 and psi 2, they contribute negative 2 pi to our final equation here. The integral over gamma, this was 0. So what's left for us to do is evaluate the integrals over big gamma 1 and the big gamma 2. And yeah, I'm just going to cheat a little bit and just evaluate the integral over the whole entire semicircle, even though we have little branch cuts here. But you can always just change the domains of your integration to each of those separate parts. It just works out the same way anyway, so let's not get too fussy about our domains and whatnot. And so I guess I'll do the integral over gamma to finish off over here. I couldn't really figure out a nice way to estimate the integral actually. It was a bit funny to do. So let's take a look at the integral over gamma, which is just gamma 1 union gamma 2 pretty much. That's going to be the integral. If we plug in the parameterization, so first of all, how do we parameterize the gamma integrals? So gamma, that is going to be z is equal to r e to the I theta, where theta, well, it could run anywhere, but let's just choose 0 to pi. And we have, let's see, dz, that's just equal to we have I times r e to the I theta. So that's what we have, and we have a d theta. So we can just plug in this parameterization. It's not too tricky. I'm just going to leave the integral blank here because it doesn't really matter what our domain is. And we're going to plug in that parameterization. That gives us the logarithm of, we have something squared and then plus 1. We have r squared e to the 2I theta. So this was our z squared before, and then we have a plus 1. And all of this is divided by, we have r e to the I theta, actually r squared e to the 2I theta, and then our dz, that becomes I r e to the I theta and d theta, and you may notice this guy and the squares over here cancel slightly, so this is going to give us the integral of logarithm of r squared, and then we have e to the 2 times I times theta, and then we have a plus 1, and all of this is divided through by, well, we have the I out to the front, and we have r e to the I theta, and then we have a d theta. And I need a new piece of chalk because this chalk has been reduced to a little pebble thing, so I need new chalk. Luckily the uni has, they have chalk here in all the rooms with blackboards, so I can just steal a bit of chalk. And yeah, we've got brand new chalk now. So how do we evaluate this? Well, what exactly happens as r approaches infinity? Well, this might be a bit of a problem, you might think, because we have r squared on the numerator and then r in the denominator. However, because that r squared is in a logarithm, it still actually grows slower than the r down here. So in fact, this is going to go to 0 if you just take r to infinity. And yeah, as I said before, I couldn't really work out a nice way to bound this if you put absolute values everywhere and use the integral inequality to bring the absolute values in over here. Couldn't really think of a nice way to bound the logarithm, or maybe there's some log inequality that I don't know yet. So if you do know how to bound that, definitely let me know down in the comments below, because yeah, I don't know how to do it. Yeah, the only way I can think of is, well, very unrigorous, and it just involves taking the limit as r approaches infinity inside of the integrand. So if you take r to infinity over here, what are you going to get? You're going to get, well, the I is still there, but that doesn't really matter, the integral. And we have, let's just do 1 over e to the I theta. If you differentiate the top there, you're going to get 1 over r squared, and then e to the 2I theta, and then plus 1, and then because of chain rule, you also have, I believe that's 2r, and then some e to the I theta here as well. And then if you differentiate the denominator, that is going to be, well, e to the I theta. So we have, yeah, 1 over e to the I theta. Okay, but then, yeah, a bunch of things cancel, and then, yeah, as I said before, the denominator will outgrow the numerator because we have an r squared down here. You can put it d theta if you want to. So this really does indeed go to 0. That's a very unrigorous way of doing it because I assume you can put the limit inside of the integral. You probably could do that if you're able to find an upper bound for the integrands there, which I was not able to find. But I'm just going to trust that this goes to 0, and yeah, everything just works out nicely in the end anyways. So finally, these guys, so integrals, the gamma integrals here, these evaluate to 0. So we're just adding 0 to this final expression. So pretty much, well, basically therefore, in the end, I is equal to 2 pi. So the contribution to the integral, or the contour, really comes from these two parts over here, and we were really lucky that the logs cancelled. So we got some nice integral out of these two parts here, and that's how we managed to do it. So that's pretty much all for this integral. I actually got this from Stack Exchange. I forgot to mention that at the start. So this was, I think I saw this picture from one of the solutions. I think it was Ron Gordon, probably. He posted this picture of the contour, and he just gave a very rough solution, like 2 lines on Stack Exchange. So hopefully this is a bit more of an in-depth solution here. So yeah, interesting solution. Even though we have logarithms and weird stuff up there, we still end up with a nice answer of 2 pi. So that's pretty cool. So that's all for this video. If you guys have any contour integral suggestions or complex analysis things you want me to do, feel free to yeah, email me or post something in the comments below. And yeah, I'll probably end up doing it if I can do it. So that's all for today. Hopefully you guys enjoy. And up until the next one, have yourselves a wonderful day. And yeah, I'll see everyone later. Bye-bye.